All right, welcome back, everybody. We're back in Chapter 2, talking about significant figures and mathematical operations. So in this section, we'll talk about, for numbers that involve significant figures, how to determine how many significant figures are in the number. And then when you perform a mathematical operation on that number, like you multiply it, divide it, add it, or subtract it, how to know how many sig figs or how many digits you should include in that final answer. Because we always want to round our final answers so that the number of digits in the final answer reflects the amount of precision or certainty that we had in our original value. So there are some guidelines for determining the significant figures in calculations. So if you have a number and you're going to be performing a calculation on it, and that number is from a measurement, that means it has sig figs, you need to be able to count how many sig figs are in that number. So in numbers, any digit that's not 0 is always going to be significant. So for example, let's say we have 1, 2, 3 that has 3 sig figs. All those non-zero numbers are significant. 1.278 that has 4 sig figs. So all the rest of the guidelines for sig figs are dealing with what do you do with the zeros that are in a number? How can you tell if a 0 that's in a number that's a measurement or has some uncertainty in it? How do you tell if the zeros are sig figs or not? So the first one of the guidelines dealing with zeros is what to do with zeros that are between non-zero digits. So anytime you have a 0 between two non-zero digits, the confined zeros are going to be significant. So for example, let's say we have 1205. This 0 here is a confined 0, so it counts as a significant figure, and so we have 4 sig figs in this number. If we have 1.032, this 0 is a confined 0, it's between two non-zero digits, so we have 4 sig figs in this number. The next guideline says that zeros before any non-zero digits are not significant. These are called leading zeros. So an example of this would be a decimal value like 0.0013. All of these zeros here come before the first non-zero digit, and so they're not significant. They're just placeholders. And so this number has 2 sig figs. 0.000003. All of these zeros come before the first non-zero digit, so this just has 1 sig fig. Just the 3 is significant. The next guideline is about zeros at the end of a number. Zeros at the end of a number are significant if they are after the decimal point, and these are called trailing zeros. So for example, if you have 125.000, because all of these zeros come after the decimal point, they're counted as significant. So this number would have 6 sig figs. Let's do another example. Let's say we have 0.00120. So these first 3 numbers come before the first non-zero digit, so they're leading zeros, so they don't count. But this last digit is after a non-zero number, and it is in a number with a decimal point. We had a decimal point here, so this one counts. So this number would have 3 sig figs. Next one, zeros at the end of a number with a decimal point are significant, and zeros at the end of a number without a decimal point are what we call ambiguous. And we want to use scientific notation to make those zeros unambiguous. So it's really important when writing numbers in science that if you intend for the zeros at the end of a number to be significant, you have to include the decimal point. And if you don't intend for them to be significant, then you can leave the decimal point off. It's always best to write them in scientific notation because that takes the guesswork out of it. You always sometimes wonder if the decimal point is left off, like, did they mean to do that or did they just forget to put the decimal point down? And it really matters. And so it's important that you get in good habits of, if you intend to have a decimal point, you include it. And if you don't have a decimal point, we're going to assume that it's explicitly not included, that you're needing to leave it off. So an example of this one, if you have 1200 with the decimal point, these zeros that come before the decimal point are significant. So this would have 4 sig figs. But if you have 1200 without a decimal point, no decimal, that would only have 2 sig figs. What you're saying is that these 2 zeros here are just placeholders. They're not significant. So the only significant digits are the 1 and the 2, so you'd only have 2 sig figs. By writing things in scientific notation, when you write a number in scientific notation, you only include the sig figs in the scientific notation. And so writing these types of numbers in scientific notation takes a lot of the guesswork out of it. So if we wrote our first number in scientific notation, 1200 with a decimal point, it'd be 1.200 times 10 to the third. And you can see that we have 4 sig figs because there's 4 digits in the scientific notation. But if we wrote 1200 with no decimal point in scientific notation, we have to imagine that it's there in order to move it into scientific notation. We imagine that it's there just to get the number in scientific notation. But when we write it in scientific notation, it's written as 1.2 times 10 to the third. And that has 2 sig figs. So be sure to either explicitly, include the decimal point or purposely not include it because it matters. And so we're going to be, from this point on, really looking if you include that decimal point or don't include it. And we're going to assume that whether it's there or not, it's intentional. So this is from your textbook. It's a summary of how to determine the number of sig figs in a number. So anything that's non-zero, that's always going to be significant. And then for zeros, there's kind of 3 types. There's leading zeros. Those are at the beginning of a number. They're not significant. There's confined zeros. Any zeros between 2 non-zero digits are always going to be significant. And then there's trailing zeros. And these ones are only significant if the number has an explicitly shown decimal point. So when we take measurements, numbers that have uncertainty, and we add them, subtract them, multiply or divide them, we have to keep track of the sig figs. And this is to ensure that the final answer doesn't appear to be more or less precise than the measurements allow. You basically can't make up numbers. You can't start out with a really imprecise measuring device, multiply a measurement you got from that device by 2 and come up with a really precise answer. It wouldn't be honestly representing that data. So we as scientists have to take numbers from our calculators and round them to the proper number of sig figs. So your calculator doesn't know about sig figs. It's going to display as many digits as it can typically fit on its screen. So it's up to us to take the numbers from our calculators after we perform mathematical operations and round them to the appropriate number of sig figs. So let's first talk about rounding numbers with sig figs. So if the first non-significant digit that you're going to be rounding is 4 or less, you want to exclude it and all of the following digits. So for example, let's say we have the number 1.2345, and we want to round that number to 3 sig figs. That means our last sig fig is the 3, and we look to the right, it's a 4, so we're going to cut off those non-significant numbers, and we're going to leave the 3 as a 3. If the first non-significant digit is 5 or greater, you exclude it and all the following digits, but you're going to round up the last significant digit. So for example, if we have 1.456 and we want to round it to 3 sig figs, you count over 3 sig figs. Here's 1, 2, 3. So we're going to be cutting it off at the 5 or in the hundredths place. You look to the right. To the right of that is the 6. So it's the first non-significant digit is the 6, and it's greater than or equal to 5. So we're going to round this 5 up to a 6. So you get 1.46, and then all the other digits get cut off because we want our final answer to just have 3 sig figs. If the first digit to be excluded is before the decimal point, you're going to follow the rules above, but put zeros in place of the drop digits as placeholders. So let's say you have 567,890, and you want to round that to 3 sig figs. You count over 3 sig figs to find out where your last digit's going to be located. So let's count over 1, 2, 3. So the thousands place is going to be where your last number is located. You look to the right, it's an 8. So you're going to round the 7 up to an 8, and then you're going to drop everything else. But since this number is before the decimal point, this number that you're rounding, you have to fill in these drop spots with zeros. So you get 568,000 with zeros filled in with the digits that you dropped. And we purposely did not include a decimal point here. If we had included a decimal point, then we would have 6 sig figs. But by excluding the decimal point, our only sig figs are the 5, the 6, and the 8. It would have been even better to write this as 5.68 times 10 to the 5th. And then we can clearly see that we have 3 sig figs. So now let's get to the mathematical operations. So whenever you do multiplication or division with numbers that include sig figs, anytime you have a measurement or a number with uncertainty, to figure out how you round your final answer, you have to count the number of sig figs in each of the things that you're multiplying or dividing. And then whatever measurement or number has the fewest sig figs, that will limit the number of sig figs you get in your final answer. So if we look at the first example, we have 1.5, which has 2 sig figs, multiplied by 2.001, which has 4 sig figs, to get on your calculator 3.0015. But because this is multiplication or division, we can't keep all these digits. Your calculator might display even more. We have to round it to show how precise our original measurements were, to make sure we're not adding extra numbers or accidentally dropping numbers that are important. So our measurement that had the fewest sig figs was this 1.5 with 2 sig figs. So our final answer can only have 2 sig figs, which means it's going to get cut off at this 0 in the tenths place. So we look to the right to see if we need to round it. We don't have to round it up. We just drop off everything that's to the right of the last sig fig to get 3.0 as our final answer. In the second example, we have 4.05 divided by 0.0003. So we have 3 sig figs in 4.05. I can write that a little bit better. And in 0.0003, how many sig figs do we have in this one? Do these zeros count? They're not going to count because they're leading zeros. They're to the left of a non-zero digit. So they're just placeholders, but they're not significant. So we only have 1 sig fig in that part of the mathematical operation. So our final answer is going to be limited to 1 sig fig. So when I do this, I get, let's see, 4.05 divided by 0.0003. I get 13,500 on my calculator. But now it's up to me to round this to the proper number of sig figs if this is my final answer. So I'm supposed to have only 1 sig fig because my measurement with the fewest number of sig figs only had 1 sig fig, so my answer can only have 1 sig fig. So I have to cut it off at the 1. So I'm going to look over to the right. It's a 3, so I'm going to leave the 1 as a 1, and I'm going to fill in everything else with zeros. It only has 1 sig fig, so I'm purposely going to exclude the decimal point which means all these zeros are just placeholders. They're not significant. But an even better way to write this answer would be 1 times 10 to the 5th. And now we can clearly see that we just have one sig fig. So with multiplication and division, when you do a multiplication or division operation, your final answer is limited by the number in your operation that had the fewest number of sig figs. So I always like to look at all my numbers I'm going to be multiplying or dividing and just pencil in or write in the number of sig figs that each one has, so I can quickly identify, okay, my final answer is going to be rounded to 1 sig fig or 2 sig figs. Next is addition and subtraction. Addition and subtraction is a little different than multiplication and division. Instead of rounding your answer based on the measurement with the fewest sig figs overall, you round your final answer based on the measurement with the fewest digits to the right of the decimal point. So this is basing your final answer on that measurement with the least amount of precision to determine where to round your final answer. So if we look at example 1, we have 4.7 plus 2.45. So 4.7 ends in the tenths place, and 2.45, its last digit, is in the hundredths place. So the least amount of precision is in this 4.7 measurement. It only goes out to the tenths place. 2.45 is more precise because it goes all the way out to the hundredths place. It has more digits to the right of the decimal point. So we have to limit our final answer based on the measurement that was the least precise, which is the one that goes out to the tenths place, which means that our final answer is going to be rounded at the tenths place. So you get 7.15 on your calculator when you do this, but then you have to look at the 7.15 and recognize that it gets cut off at the 1. So you look to the right and you round that the 1 to a 2, because to the right of it is a 5, and you end up with 7.2 as your final answer. Let's look at example 2. We have 4.5, this ends in the tenths place, minus 0.0002. So this ends all the way out in the 10 thousandths place. So the measurement that's the least precise, that has the fewest digits to the right of the decimal point, is 4.5, which ends in the tenths place, which means that our final answer will also have to end in the tenths place. So when you take 4.5 minus 0.0002 on your calculator, you get 4.4998, but we have to round this to the tenths place. So this 4 here in the tenths place is our last sig fig. We look to the right and it's a 9, so we have to round this to 4.5, which the number didn't essentially change. So again, to kind of summarize the mathematical operation rules for sig figs, in multiplication and division, the measurement with the fewest sig figs, you just count up the total number of sig figs. The measurement with the fewest sig figs is going to determine the number of sig figs in the final answer. In addition and subtraction, the measurement with the fewest significant figures past the decimal point, meaning the measurement that was the least precise, is going to limit the number of significant figures in the final answer. So we've been talking about how to handle inexact numbers, like measurements, when we do mathematical operations. What about exact numbers? Well, exact numbers don't have any uncertainty. And because they don't have any uncertainty, we can assign them an infinite number of sig figs, which means that they won't limit the number of sig figs in your final answer. So let's say we have 12 eggs we want to line up end to end, and we measured that the average length of one egg is 7.34 centimeters. The length of that line of eggs would be 88.08 centimeters. But we have to round this number to the right number of sig figs. In this case, 12 eggs is a counted number. Counted, so this is exact. And sometimes I just write this as infinite sig figs. So if it has infinite sig figs, it won't affect the final answer. So the only thing that's going to affect our final answer is this measured value of 7.34 centimeters per egg. 7.34 centimeters per egg has 3 sig figs. And this is a multiplication problem. You're taking 12 eggs times 7.34 centimeters per egg. So we're going to use the rules for multiplication to round our final answer. And the rules for multiplication says you round your final answer to whatever number that has uncertainty, whatever measured value has the fewest sig figs. So we have infinite sig figs compared to 3 sig figs. So our final answer is going to be rounded to 3 sig figs. So you get 88.08. You look to the right of the last sig fig, and it needs to be rounded up to finally get 88.1 centimeters. And you can check, it has 3 sig figs. So if you're dealing with a problem where you have some exact numbers, and remember all those metric system prefix conversions, those are all exact numbers, you don't have to take those into account when you're figuring out where to cut off your sig figs. Exact numbers have infinite sig figs, so they'll never be your limiting factor in sig figs when you're counting them up. Okay, so calculations with multiple operations. Like, what do you do if you have a problem that involves some multiplication, some division, some addition, some subtraction? So when you have a calculation with multiple operations, you want to perform the operations inside the parentheses first and keep track of the sig figs for that operation by drawing a line under or over the last sig fig in that answer. So you kind of keep track of your sig figs step by step. And I like to draw just a little line under or over. Some people put a star, whatever works for you. But the key is that you keep track of the sig figs, but you wait to do your rounding until you get to the very last operation. So you only actually round your final answer, but you keep tabs on the sig figs all the way through. And each step of the way, you follow the rules for that mathematical operation. So when you're doing a multiplication step, you follow the sig fig rules for multiplication to keep track of where the sig fig would be, the last sig fig for that part of the operation. And then you do the next operation, you follow the rules for that operation and keep track of the sig figs. So for example, if we have 3.5 plus 2.456 times 9.123, assume all of these numbers are based on measurements, they all have sig figs. So we do what's inside the parentheses first. Inside the parentheses is an addition problem, so we follow the rules for sig figs for addition, which means that we're going to round our final answer, if we were done with the problem, based on the measurement that had the least precision. So in this case, we have 3.5, which ends in the tenths place, and 2.456, which end in the thousandths place. So we need to round our answer for this part of the problem to the tenths place. What we're going to actually do is calculate the answer to this part of the problem, and then we're going to just put a little line over our last sig fig, which will be in the tenths place, but we're going to wait to round the answer until the very end. So when you add those two together, you get 5.956. And I just put a little line and highlighted here that 9 because that's in the tenths place. That's our last sig fig based on the addition step. So now we need to do the next part of the problem, which is taking the 5.956 times 9.123. And we're just keeping tabs on where our sig figs are. So we have 5.956 times 9.123. This is a multiplication step. So for multiplication or division, you have to count the sig figs in each number. So here we have 2 sig figs because we would be cutting it off at the 9 if that was the end of the problem, but it's not. And in the 9.123, we have 4 sig figs. So after we do this multiplication step, the rules for multiplication division say that your final answer is rounded to the number of sig figs as whatever number had the fewest sig figs. So our number with the fewest sig figs was this 5.956 with 2. So our final answer is rounded to 2 sig figs. If we weren't done yet, if there was another step in the calculation, we just keep tabs on our last sig fig. we'd underline or highlight or put a star over the 4, but we'd wait to round the answer until we got to the very end. So you round 54.336588, etc. on your calculator to 2 sig figs. And so for this problem, the final answer is 54. So keys to remember: do what's inside the parentheses first and then work your way out. For each step, you follow the sig fig rules for that particular type of operation. So when you're doing addition or subtraction, you follow the sig fig rules for addition or subtraction. And then you keep track of where your last sig fig is based on that rule. And then you go on to the next step in the problem and you follow the sig fig rules for that step. And you keep doing that until you get to the last step. And then at the very final step, that's when you do your rounding. And this is to make sure that you don't round too soon and you end up getting a value at the end that's not actually accurate. Okay, let's do a couple practice problems. So in which of the following is the number correctly rounded to give 3 sig figs? Is it A, B, C, or none of them? No correct response. So hopefully you come up with B. 32.57 becomes 32.6. The reason it's not A is because when you round 0.01136 to 3 sig figs, your last sig fig would be the 3. You count over the number of sig figs. These zeros are leading zeros, so they don't count. So you count 1, 2, 3 sig figs over. You look to the right and it's greater than or equal to 5. So this 3 should have been rounded to a 4. So that's why this is not the right answer. 32.57, you want to round that to 3 sig figs. So you count 1, 2, 3 sig figs over. You look to the right. So the 5 should get rounded to a 6, which is what happened. And here, 1.2001, you count 1, 2, 3 sig figs over. You look to the right. It's a 0, so it should stay as 1.20. You shouldn't have to round that one up. Okay, next one. When rounded to 3 sig figs, the number of 43,267 becomes what? So to solve this one, you want to count 3 sig figs over. 1, 2, 3. Look to the right. So you should be rounding the 2 to a 3. So you're going to get 433. No, you'd be missing some extra placeholders. 43,267. No, you didn't do any rounding on that one. 43,300 without a decimal point, or 43,300 with a decimal point. Well, you want to round it to 3 sig figs. So this one has 3 sig figs because without the decimal point, these zeros are just placeholders. So your only sig figs are these 3. But 43,300 with a decimal point, that has 5 sig figs. So the correct answer on this one is going to be C. 43,300 without a decimal point. So let's do a few practice problems using sig figs and calculations. What I suggest you do is work on each problem on your own for 2 minutes. Pause the video while you work, and then resume it when you're ready to look at us working through them together. So hopefully you've taken some time to pause the video, work through problem 1, problem 2, and problem 3 on your own. And then I'll go over to a whiteboard now to work through these with you as well. Okay, so problem 1. We had 89.3 times 77.0 times 0.080. So this is a problem that involves all multiplication. And so you're going to just follow the rules for multiplication or division. So to do that, you want to count how many sig figs are in each number. So we have 3 sig figs in 89.3. We have 3 sig figs in 77.0. This 0 counts because it's after the decimal point and after a non-zero digit. And then in 0.080, we only have 2 sig figs. These 2 zeros that come before a non-zero digit instead of after, they don't count. They're leading zeros. So we have 2 sig figs here. So when you plug this into your calculator isn't smart enough to round sig figs for you. So it's going to give you an answer, something along the lines of 550.088. But we need to round this to 2 sig figs because we know that based on our numbers and our measurements, the number that had the least number of sig figs was 2 sig figs. So our final answer should have 2 sig figs. So we count over 1, 2. So this 5 here is our last sig fig. We look to the right and it's a 0, so the 5 doesn't get rounded. So your final answer, you get 550 without a decimal point, because if you put a decimal point here, it would show that this 0 counted as significant, and we don't want it to. We only want to have 2 sig figs. But it's even better if you do 5.5 times 10 to the 2, because then it's very easy to see that you have 2 sig figs. Okay, problem 2. So this is a multi-step one. Oh, no, just one step, sorry. I'm getting ahead to problem 3. So problem 2 is an addition problem. You have 0.005 plus 0.0987. It's an addition or subtraction problem, so your final answer is going to be rounded based on whatever value you're adding or subtracting that has the fewest number of digits past the decimal point or the least precision. So our first number goes out to the thousands place. And our second number goes out to the 10,000s place. So the number with the least amount of precision that has the fewest digits to the right of the decimal point is the 0.005 in the thousands place. So that means our final answer is going to be rounded to the thousands place. So when I do this on my calculator and add these two up, I get 0.1037. But we know based on our number that had the least precision or the fewest digits to the right of the decimal point that we need to round this at the thousands place. So that's that 3. We look to the right, it's greater than or equal to 5. So we're going to have to round that 3 up to a 4. So your final answer is 0.104. Okay, problem 3. Problem 3, we had a multi-step problem. So we had 249.362 plus 41 divided by 63.498. So to start this problem, we want to do the part that's inside the parentheses first and follow the sig fig rules for that operation, which in this case is addition. And then once we get an answer there, we're going to just keep track of where the last sig fig is, but we're not going to round anything. We'll move on to the next step and follow the sig fig rules for the next step. So let's take this first step down here. We'll do 249.362 plus 41. And if we're doing addition or subtraction, we're going to cut off our final answer or intermediate answer in this case based on the number with the least precision. So this 249.362 goes after the thousands place. And 41 just stops at the ones place. So 41 is less precise than 249.362. So we're going to have our last sig fig once we compute the answer to this in the ones place. So if you add these up, I get 290.362. And I'm going to keep track that my last sig fig should be in the ones place based on the sig fig rules for this addition step, but I'm not going to round that value yet. What I'm going to do is I'm going to keep it in my calculator just like this, and then I'm going to do the next step, divided by 63.498. And now my last step is division, so I'm going to follow the rules for multiplication or division. So if I count up my sig figs, I have 3 sig figs in 290.362, because my last sig fig should be this 0 here. So I have 1, 2, 3. And then 63.498, I have 5 sig figs. So my final answer, when we round, the final answer should have 3 sig figs. So on my calculator, I get 4.5727 and a bunch more digits. But we need to round that to 3 sig figs, which is this 7 here. So we look to the right and it's a 2. So we're going to leave that 7 as a 7 and cut off all the other digits, not include them. So we get for our final answer 4.57. So again, the key to getting this one right is following the rules for sig figs in the first step, recognizing that 41, that measurement had the least precision, it stopped at the ones place. So whatever answer we got from this step, our last sig fig was in the ones place, but we waited to round it until the very end. So we left all these other digits. And if you're doing this in your calculator, just leave this number up on your calculator so you don't accidentally round, and then go on to the next step and just keep tabs that you had 3 sig figs at the end of this step. Okay, so that's it for this section. We covered a lot of material, how to count the number of sig figs in numbers, how to round sig figs, and then how to do different types of calculations, addition, subtraction, multiplication, and division, as well as multi-step calculations with keeping track of the number of sig figs. Please practice this. You'll get a lot of practice in it in the Chapter 2 homework. And if you'd like additional practice, feel free to reach out to me and I'm happy to give you additional practice problems. Doing these types of calculations is something you're going to do in this class over and over from this point on. And it's expected that you'll know how to do calculations that involve measurements, both in the lecture and the lab portions of the class, and round your final answers to the appropriate number of sig figs. So make sure you spend some time getting to know this material, and feel free to reach out if you have any questions. All right, thanks. I'll see you next time.